Hi everyone, welcome to this webinar, which is part 2 regarding the analysis and design of a steel hull with SCIA Engineer. I hope you all can hear me. If not, feel free to put it into the chat box. Also, you can use that chat box or questions box to ask your questions during the webinar. Because the second part of this webinar will be a Q&A, so we will try to answer all of your questions. Great, so let's just start with it. Let me just minimize this window. Okay. Today we are going to talk about 3 topics related to steel. The first one will be the stability analysis of steel structures. This was already handled in the first part, but it's also needed for the second order analysis. So that's why I've put it also in this session. The second part will be the second order analysis of steel structures. I will talk about a general overview of second order analysis, the effect of the imperfections on the bending moments, and also a workflow will be presented so that you guys can use it directly in your project. And the third and last part will be the steel SLS check, which is a relative deformation check. Again, there I will give an overview about check and also a workflow for that SLS check. So first things first, let's start with stability. So stability analysis of steel structures. The stability analysis is usually used for determining the buckling shape of your structure. This gives you some insights on how the structure will fail. It also gives you information about, besides the buckling shape. So here you can see how it will fail for a given load, which are the weak elements of your structures, and if you know them, then you can adjust them accordingly, effectively as well. So you can only you can reinforce it on these 2 positions, and maybe also in this position use a bigger cross section, for example. Another thing it can provide is the so-called alpha critical value. In SCIA Engineer, it's called the critical load coefficient, or the alpha critical. This is a sort of amplification factor. It basically means that your normal force in your member, for example, or in your structure, multiplied with this value, is in fact your N critical, your critical Euler load. Under this critical load, you will get the flexural buckling instability. And this is for a given stability combination S2. And in this case, we've determined 10 eigenmodes with their corresponding buckling shapes. So the first buckling shape occurs at this alpha critical value, the second one at this one, and so on. It's also specified in the Eurocode, and it's also something very important when the user wants to know if he or she is obliged to execute a second order analysis or not. Maybe I can quickly jump to the Eurocode. It's explained on the chapter 5.2. This is that alpha critical value, which can be obtained by executing a stability calculation. I will show it in a moment in SCIA Engineer how to do it. But yeah, you see it right here. So for an elastic analysis, your alpha critical value needs to be bigger than 10. If it's bigger than 10, you can get away with a first order analysis. If it's lower than 10, you are in fact obliged by Eurocode 3 to execute a second order analysis. You can always do a second order analysis regardless of the value, but you are obliged to do it if it's lower than 10. And if it's higher, then you can get away with a fast first order analysis. This is the case of an elastic analysis, and for a plastic analysis, for example, if you take into account plastic hinges and things along those lines in your model, then the value is 15. Okay, so let's go back to the presentation. So besides the buckling shape, we also obtain the alpha critical value, which is basically also step one of your second order analysis. Are we obliged or not obliged to do a second order analysis? Well, in order to know that, you'll need to do a stability analysis. And the third one is, once you know that alpha critical value, it's nothing more than multiplying it with the normal force in your member to obtain your N critical, your critical Euler load. Once you know your critical Euler load, you can use Euler's formula to derive the buckling factor, because this is the formula for your N critical. This is a material property, your E modulus, your second moment of area, pi. The length of your span, you know this value thanks to your alpha critical. Then the K, your buckling factor, Ky or Kz, is the only unknown, which can be then derived by means of the following formula. Also, this one will be shown in SCIA Engineer. There is a way to retrieve it automatically by just assigning stability member data. That's also what I try to explain right here. So this is just an example of a frame. We see a certain normal force. And we see also, I intentionally try to make only this rafter buckle by putting a compression force on it. And this gives you this normal force. I will only consider segment 4, which is this part right here. In the other directions, there are also members on these positions. So segment 4 has a normal force of 0.9607 kilonewtons. The alpha critical, which leads to flexural buckling around the strong axis, is 2,141. The alpha critical that leads to flexural buckling around the weak axis, so in the depth direction, is 14,177. So if you basically have to select them manually in the stability member data, and that's all you need to do in order to obtain the buckling factors precisely. So if I go further, this is just a manual calculation in ModCut with the same data, leading us to a buckling factor of Ky of 0.72 and a Kz of 0.98. And we see the same results for segment 4 for Ky 0.72 and for Kz 0.98. This is just to give you guys an idea of the background behind the algorithm. For the user itself, is just add the stability member data, select the proper stability combinations, and that's it. So here we can see an overview of the workflow. So the stability analysis is then used for determining your alpha critical, your buckling shape, or your buckling factor. The first step you'll need to do is you need to activate the functionality stability. You cannot execute the stability analysis without creating stability combinations. It's also very important to mention that you'll need to refine your mesh settings. I would advise to use a mesh setting of 5 or 10 as a minimum, because if you only have, for example, a column with a mesh of 2, your half sinus shape will then be described as a straight line that goes like this, bilinear line. If you have 3, then it's a bit more precise, but if you have 5 or 10, then that curve gets described much more precise. So 5 or 10 is always a good approach to as a mesh size for your 1D members. The next step is you need to define your number of eigenmodes. It could be that the member you want to see buckle is not buckling. I will show it in a moment how to enforce it, but that can still happen. So that means you'll need to increase the number of buckling shapes you want to retrieve per stability combination. So each stability combination will have a certain number of eigenmodes. Once you've done that in the solver setup, you can run the calculation and evaluate the results. And with evaluate the results, it's basically going to the results service and having a look at the different buckling shapes per stability combination. And as mentioned, it can happen that the member you want to see buckle is not buckling. In that case, you'll need to increase the number of eigenmodes until it buckles. Okay, I can maybe go to SCIA Engineer. So let me switch. So here's SCIA Engineer. As indicated, the first step for this project, if you want to do a stability analysis, we'll need to activate the functionality stability, which can be found under functionality in the project data dialog. Once that is done, we'll need to create stability combinations. If you do not create these, you cannot execute the stability analysis. So under stability combinations, you'll see that I've already prepared two stability combinations, but I can just quickly delete them just to give you guys an idea how it should be done from scratch. So in this case, those two stability combinations were actually created to make certain members of the structure buckle. To be more specific, this rafter and this column. How do you do that? Let me just quickly change the view. So I have a saved selection to select that frame, and let me isolate them. So if I want to make this member buckle, I just have to add compression force here and there, for example, and only add that load case to a stability combination, because that stability combination only contains that compression force. Therefore, this will be the only part that will buckle during your stability analysis. And that's what I've basically done by means of the following load cases. Let me make them visible. So here we see compression on the rafter, and the other one is on the column. So a compression on the column to make that one buckle. So once I've added these loads, I go to stability combinations. I say, okay, I want to make one for the rafter. So let me just add that one to the stability combination. Okay, call it S1 rafter, like that. I'll make another one, new, which only contains the one for the column. Add. I'll call that one S2 column. Okay, so now I have two stability combinations that can be used for analyzing these two elements in order to retrieve their buckling factor. Before I continue with the analysis, let me just also add one that is coming from your combinations to get more insight on how the entire structure will buckle. So I could create them directly from that same window from scratch by adding all those load cases and maybe put the proper coefficient before every load case. That's a lot of manual work. Another way and a better way to do it is just go to your combinations. These are your Eurocode combinations. You can explode them to linear in order to import those linear ones into the stability combinations. It's not directly possible to import an envelope of combinations as a stability combination. So an intermediate step is needed. You just have to click, select the one and click on explode to linear. Click on yes. So basically this combination has these 8 combinations as its content. And I will only pick one. I will just use this one, for example, the 5th one, which contains all load cases. And that can be done by going back to stability combinations. And here you have the button, new from linear combinations. So I will use a linear combination and in fact convert this linear combination into a stability combination as well. So it will still remain there, but there will be a duplication as a stability combination. So just select it and click on close, and you will see it appear in this with the same content. So close, but as a stability combination. So I'll call this one S3, which basically comes from ULS B5, for example. In reality, if you want to consider all combinations, you would need to import them all. So you would need to select them all and click on close. Then you will get the full picture of the structure. But for this webinar, I will only use one, which is this one. Not sure what this one is doing here. Close. Okay. So now I have my stability combinations, which means I can start the analysis. But keep in mind, your mesh settings has to be bigger than 1, 5 or 10. The default is 10, so that's good enough. And the number of eigenmodes can be specified in your solver setting. You can also specify which solver you want to use. I recommend the polynomial one. It's the most robust one, but you'll also have other options at your disposal. At the end, they should give all the same result. It's just a different way of solving these equations. But the polynomial for me has proven to be the most stable one. And here you can select the number of eigenmodes per stability combination you want to calculate. In my given example, I will use 70. And I only have to take it on right here and start the calculation. So now it's executing a linear calculation and afterwards a linear stability calculation. So that's what you see right now. The number of eigenvalues is 70. It's going through the first one. Now the second one. So the more you have in combination with the number of eigenvalues, the more time it could take. And this is the third one. It should be the last one. Okay, it went through it. So I click on OK. And now we can go and have a look at the results. So I go to results, and the place you'll need to be is at 3D displacements, and make sure to activate wireframe. Otherwise, it will do it in a 3D way, showing the displacements, which is it takes some time. It's a bit heavy on the computer. So I'll put wireframe here, and of course, we are only interested in the stability combinations, so I will use stability combinations as a type of load. And here you can see the different stability combinations we have. Notice that S1 has 70 eigenmodes. That's the setting we've set in the solver setup. So every stability combination will have 70 eigenmodes. So S2 the same, and S3 also the same. So let's have a look at S1, the first one, which is the rafter. So I would expect that this rafter will buckle. I will just set it to all. I'm only interested in this frame. So I'll click on refresh. So this is the first eigenmode. So it will buckle under a normal force of, let's say, 1 kilonewton multiplied with 2005 as your alpha critical. So 2005 kilonewtons, you will get this as the first buckling shape. Basically buckling around the weak axis. That's what we see right here. If I go to the second eigenmode, which is just a bit higher, 2038, click on refresh, we see buckling around the strong axis. And so if I just change the viewpoint, you can see it's clearly buckling around the strong axis. And you can also show it in an animation window if you want to get a better idea on how it behaves. So here you can see how it's buckling in fact. You can do this also for the entire structure. I will do it in a moment for the third stability combination. So we now know that S1 could be used for calculating KZ, and S1/2 can be used for calculating KY. So let's keep that one in mind. Let's have a look at the second one, S2, which should cause buckling of the column. Click on refresh. We see the column buckling under a load of, let's say, 1793. Of course, in your situation, you will, for example, use your reload, and this value could be very low. It's always the buckling load is in fact this multiplied with your average normal force. But we see here weak axis buckling for S21, and for S22, we see strong axis buckling. That's what we see right here. And also this can be shown in an animation window to get some insights. So here you see how it will buckle for that given load. The rafter is just following the buckling shape of the column. For the third one, let's just change the view. We want to see the entire structure. So like this, for example. And then we go to S3. And if I remember correctly, these were all individual buckling shapes. So let me just randomly pick one, click on refresh. It's not a global buckling shape. It's basically the buckling of these members, but not of the entire structure. So if I take another one, you will see the same, something similar, but for another member. But if I go to the number 63, if I'm correct, it should be something global. And that's what you see right here. This is a more global buckling shape. And in fact, it's also described in the Eurocode. You could use this shape, and it will be mentioned in the next slides. You could use this shape as your initial imperfection of your structure for your second order analysis. This is in fact the most precise approach you could do. You could execute in a second order analysis in SCIA Engineer. And by doing that, the Eurocode also states that you shouldn't, there's no need to consider flexural buckling. So once you do this, the flexural buckling check becomes obsolete, which means the whole KY, KZ buckling factors is no longer relevant. That's the reward you get when you do a real second order analysis. You can forget about the KY and the KZ factors. I will show that also in the next steps. So we know that S1 and S2 can be used for calculating your buckling factors. So if I go to steel, I can do this by means of the stability member data. So I can say, okay, for this rafter, I know that S11 causes weak axis buckling. So I will use S11 for determining KZ. I know that S12 causes strong axis buckling. So I can use that one for KY. And here you can top it off. So here you could say, even if it finds a value of, let's say, 15, top it off at 10. That's just an extra feature you have at your disposal. So I click on OK. It asks me to select the proper beam, so this one. And you will see the label appear. So this is the stability member data. And we can also directly see all the buckling factors for each segment. So this is the first segment, this is the second segment, the third, the fourth. You see here, for the y-axis, it's all the same. It's all 0.56, besides at the beginning and at the end. This is because your cross-section is different here. You have a different IY, second moment of area, due to this variable cross-section. But here it's constant, which leads us to a constant value of the KY. And it's also one big span. So it's calculated per span. For Z, for the Z, there are multiple spans. This is, for example, span 1, span 2, span 3. Maybe I can show it a bit more clearer if I show you those spans. Okay. So opening the buckling settings, and there you can see the spans. So for KY, we see it's one big span, because we only have a solid triangle at the beginning and at the end. These are not activated, so it's one big span. For KZ, that's not the case. Thanks to these members that are here, they make they reduce the big span into smaller spans, which is beneficial. It increases your buckling resistance. But that also means for calculating the buckling factor from the stability, it will only look at this span for obtaining the average normal force. It will use the average normal force of this span for calculating it here, the average normal force of this span for calculating it here, and so on. Okay, the same can be done for the column. It's basically the same steps. So stability member data, I know that the column buckles under S21. No, sorry, S21 is for KZ. So let me go to KZ, S21, and S22 is for KY, which is this one. Click on OK. Select the member, this one, and we see it appear right here, and we see already the buckling factor. So this is in fact the most precise way in SCIA Engineer to calculate your buckling factors. If you just do a normal, if you just do a linear calculation, so without stability, without second order or anything else, it will use a different approach, which has its limits. The main limit is it gives good results for moment rigid connections, columns or beams connected with moment rigid or semi-rigid connections, and that are under an angle of approximately 90 degrees perpendicular. If you don't deviate from that, it gives proper results. But as soon as you have a hinge here or something else, it can give you, obscure results, weird results. You would expect, for example, 1 here and gives you a value of 4 or 5, which influences your steel coat check, because your buckling check will most probably fail in that case. So this is a way to circumvent that. A better way, which is the next thing I will explain, is just do a second order analysis, and you can forget about buckling because it's already taken into account during the analysis. So no need for the flexural buckling check. Okay, so let's go back to the presentation. That was the stability part. It will come back here also in the second order part. So let's talk about the second order analysis of steel structures in SCIA Engineer. This is a picture I've taken from Eurocode 3, in which they show how global imperfection under a certain load is visualized, and also a local imperfection by means of a bow imperfection is also visualized here. And those two imperfections can be inputted in SCIA Engineer. So let's have a look. So here you can see a comparison between first order and second order. You don't have those imperfections in the first order analysis, which is in fact in SCIA Engineer a linear calculation. The second order analysis, or non-linear calculation with imperfections, is shown here. So here you see again those two imperfections, the global one and the local one, the bow imperfection. That's what you see here, the P delta and the bow imperfection, which is shown right here. So those two imperfections will lead to extra moments. And that's what you see right here. The moment at position X is described by the following formula, so at this position. The moment at the column base is described by the following formula. So your horizontal multiplied with the length is one part of the moment, plus your compression force multiplied with the eccentricity is your second one. So those are called global and local or bow imperfections, and both can be inputted in SCIA Engineer. And this is the part that I've already explained. You are obliged to do a second order analysis when your alpha critical value is smaller than 10, and that reminds me of the fact that I haven't shown this to you guys. Where is that alpha critical value? We saw it directly in the results. We saw it here. After next to every combination, we see the alpha value, but you can also show it in a table. So if you go to results, critical load coefficients, those are the alpha values, alpha critical values. So here you can see it nicely listed in a table. Per stability combination, we see the 70 eigenmodes, and every eigenmode has a certain alpha value. So that's what you see right here. And as long as it's bigger than 10 for elastic, you can get away with a linear analysis. If it's lower than 10 for elastic, then you are obliged to do a second order. So that's one of the questions I ask myself. Does every steel user always use a stability calculation before deciding whether he or she should proceed with a linear analysis or a non-linear analysis or a second order analysis? In fact, if you follow the Eurocode strictly, you are basically obliged to always do a stability analysis in order to get this value. And then you know. So here is just an example of the effect of the imperfections on the moments. So in this example, I have a IPE 240, a simple column with compression on it. It has a length of 4 meters. It's fixed at the foot of the column, and no, sorry, the compression is in this case 100 kilonewtons. So via this way, you can calculate your bow imperfection because buckling curve A under table 5.1 of Eurocode 3 has a bow imperfection of 1 divided by 300 for elastic analysis. So 1 divided by 300 multiplied with the 4 meters is 13 millimeters. That's your bow imperfection. And for the global imperfection, yeah, the height is 4 meters. The number of columns M is 1. There's only 1. Your standard imperfection is 1 divided by 200, as mentioned in the code. This gives you an alpha H of 1 in this case, an alpha M of 1, and your inclination for your global imperfection is in that case 0.005. It's the same angle that was shown here. No need to calculate this all by yourself by hand. It's implemented within SCIA Engineer. The only thing you'll need to provide is the height of the structure, the number of columns, and you can, if needed, you can change this value. And based on those input parameters, it can calculate the global imperfection. The same for the bow imperfection. SCIA Engineer knows which bow imperfections you have. So based on that, it can calculate the E0 value. This is just an example to give you guys an idea how it works in the background. So the effect of the imperfections on the bending moments can be seen right here. So due to your inclination, due to the fact that you've added an inclination of 0.005, which is in fact 20 millimeters eccentricity, and the bow imperfection of 13.33 millimeters, you will get extra moments. So that's what you see right here. This is that 20 millimeter for your global imperfection. We'll give you this bending moment at the foot. Your bow imperfection of 13.33 millimeters will give you this bending moment. And if you combine them both, you will get at the foot 0.02. In the middle, yeah, you just have to add them up. So you get 0.023 kilonewton meters. So that's the effect of the imperfections on your bending moment. That's one part of your second order analysis. There's also another one. Due to the fact that your structure will deform further, it can happen that thanks to these bending moments, okay, you will get, yeah, thanks to these imperfections, you will get these extra moments, but it could be that your structure will move a bit further until it reaches equilibrium. Well, that extra deformation causes extra moments. And that's what you see right here. So here we see purely the, yeah, visualized the extra, the moments you get due to those extra deformations. And if you add those with the previous ones, the ones from your initial imperfections, those are the extra moments you get due to second order analysis compared with the first order analysis. So that's what you see right here. They are all added up, and yeah, it's explained here. And this is a graph that gives you guys an overview of all the different ways you can analyze a steel structure. The first one is just doing a linear calculation. You don't care about alpha. Yeah, in fact, you should care. But here we say, okay, I assume it's bigger than 10. I'll just do first order analysis, and I will do the buckling check and everything else. The other one, so path 1, as indicated, first order. Path 1B is, yeah, your alpha critical needs to be between 3 and 10. If that's the case, you can increase the moments via this, increase the sway effects with this formula. And this method also, yeah, allows you to just use a buckling factor of 1. Ky and kz is then equal to 1, and you can then execute all your checks. Then we have path 2A. And notice there's also always a reference to Eurocode 3. The articles are mentioned here. Path 2A is a second order analysis with only a global imperfection. This can only be done if your normal force is lower than 25% of your end critical. Then you can do path 2A. Then we have 2B. 2B is almost the same, but in this case, your anchored and your normal force is bigger than 25%, so you'll need to add bow imperfection. And if the member has a bow imperfection, then no need to consider flexural buckling. If the member doesn't have bow imperfection, you'll need to do the flexural buckling check with a KY or KZ equal to 1. Then we have path 2C, which is my favorite, and which is the one I will explain to you guys, because this requires a lot of effort from the user to verify whether your normal force is higher or lower than 25%. There's a lot of manual work involved in it. While 2C is basically just saying, okay, I'll apply global and local imperfection, and that's it. I shouldn't worry anymore about flexural buckling. You just apply it everywhere and be done with it. The more you go to the right, the preciser you are calculating. So 2C is more accurate than 2B, while 2B is more accurate than 2A, etc. Path 3 is, as shown at the beginning of the webinar, you do not add a global imperfection or local imperfection by means of those formulas in Eurocode 3. Instead, you just use your buckling shape, your global buckling shape of your entire structure as the imperfection. And that one has the global and the local effect in it. Yeah, that's in fact path 3. So I will explain path 2C by means of this workflow. Again, if you want to use second order analysis, it always starts with the functionalities. You have to activate the proper functionalities. So the first one you'll need to activate is nonlinearity. And the sub functionality of nonlinearity are these two. So the initial imperfections for your bow imperfections and your global imperfections, and your geometrical nonlinearity as well, to get those extra deformations due to your second order analysis and such. The next step is then you'll need to create your nonlinear combinations. Here we can use the same approach. We don't have to create them from scratch. We can just convert our linear combinations into nonlinear ones and be done with it. Then we'll need to add the global imperfections. Again, I will explain it all in a moment, just to give you guys an overview. You'll need to add your global imperfections, which is basically putting your entire structure under a certain angle. You'll need to do it or use it 4 times. You'll need to put it under an angle in the X direction, in the minus X direction, in the plus Y direction, and in the minus Y direction. So in the four directions. Those are your global ones, and then you will need to add the local bow imperfections in the buckling settings. There we can say just use the bow imperfections for elastic, and that is enough to take those into account. Once the imperfections are added and the nonlinear combinations were created, we can run the nonlinear calculation, which is in fact second order analysis following path 2C. So this path. I do have to mention this is a flowchart we've created ourselves, but in the draft of the new Eurocode, which will be released in the near future, they will also provide something similar, and they will give these paths also a certain name, which they will also use then in their articles to refer to. So in the next Eurocode, it looks much more promising, much better for the user to understand what are the different options they have in order to do a second order analysis compared with the current Eurocode, which is sometimes convoluted. Okay, so let's show it in SCIA Engineer. I'll go back to my project. No longer need this one. Okay, so the first step is, as indicated, you'll need to activate the proper functionalities, nonlinearity. Once you activate this one, you will get this sub functionalities. Those become visible, and the ones you are interested in are this one, initial imperfections for your global and local imperfections, and your geometrical nonlinearity. I've also activated beam local nonlinearity because I have wind bracings and I want them to only act under tension. So as soon as they are under compression, they get deleted from the structure as if they aren't there. They don't contribute to the global stiffness of the structure if they are under compression. Okay, so I click on OK. Next, we can define our global imperfection. This can be done by going to libraries, structure analysis, and here you will find initial deformations. We only need to define two. Let me just quickly delete this one. I've prepared them in advance. Yeah, or I can preserve them because it's nothing more than clicking on new. You'll get this dialog. You can give it a name. I recommend to give it a name X and a name Y for the two directions. So in this case, I called it idefx and idefy. You will use the type of the Eurocode as described in Article 5323. So this is, you can also do a manual input to manually define your inclination function or by means of a factor, but we are interested in the Eurocode 3 approach. This is your basic imperfection value coming from the code, so let's just use that one directly. Here you'll input the height of your structure. In my case, it's 6.8, and the number of columns per plane. Well, that's something that's open for discussion. You can say, okay, in this plane I have 8 columns, for example, while in this plane I have 3, and I want to define one for idefy, for example. Well, no, idefx, sorry. For idefx, I can see 1, 2, 3 columns, but here I have more. So which one to take? It's just using common sense. You can see that the majority in the y direction have 3 columns. So that's why I'm using 3 for idefx. That's what you see right here. And for idefy, I'm using 8. So these 8, which you see right here, which is also here, and which is also here. The only ones that have 2 in the y directions are this one, column 1, column 2, and the same for this one and here. But the majority have 8. Once you've inputted those values, the number of columns is basically that m value in the code. The height is the h value in the code. Once you have those input values, then SCIA can determine the intermediate values and the inclination function. So the intermediate alpha h, alpha m are determined here, and this is your inclination that will be used for the y direction, and this one is for the x direction. So those are now defined, but they aren't used yet. We'll need to still link them later on to the nonlinear combinations. The same needs to be done with the local imperfections. So let's just quickly do that one. Let me make the entire structure visible. I'm not interested in the wind bracings because they only work under tension, so they will never buckle. So no need to create ball imperfections for them. So let me make them invisible. So I'll just click on one of those columns, this one for example, and I will step by step define the ball imperfections for every element. I can do it in a fast way by just saying, okay, show me all the members that have one span. I can use that one as a filter. So I click on filter on that property. So all these members have one span. So, and then I go to their buckling settings like this. And here I can say, okay, for KY, I want to use ball imperfection E0Y. By default, it's set to no. So I'll have to set it to table 5.1 of Eurocode 3. It's the same table that was shown in the slide in that example. I'll have to go down, down, maybe too far. It's the same table in which you see the different ball imperfections depending on your buckling curve. So it will automatically retrieve this information from the cross section and apply the proper buckling, proper ball imperfection. So this is the one for around the YY axis, and for around the ZZ axis, the same one, table 5.1, and that's it for these members. Now that I've defined them, I can make it easier for me by hiding them so that I know which ones are remaining. Okay, let's just click on one. This one has 6 spans. Show me all the ones with 6 spans. There they are. Now I'll need to go to their buckling settings and do the same. So here I'll do the same. Table 5.1 for YY, table 5.1 for ZZ. Save. Once that is done, I can hide them as well. These have 2, I suppose. Yeah, 2. I can filter on it. Do the same again. So bow imperfection like this, same, hide. And that's it. I do have to give a remark. Due to the fact that I've taken all of these members together, it's just a fast approach, but it needs some refinement. Due to the fact that I've taken them all together, you will see that there is still a flaw in my approach. It definitely speeds it up, but there is a flaw. It means all these members assume that they have a buckling restraint in the vertical direction here and here because there are columns here, but they are missing here. So it's not correct to apply BG2 for these members. So basically, I can do the following. I can deactivate them so that BG2 is still applicable, valid for these members, but not for these ones. These ones will get dedicated ones. I'll need to do the same for this one as well because it has a column here in the middle, while these don't have a column in the middle. So let me just quickly clean that one up. Save. And I can give these two dedicated ones by switching them to default and then clicking on the three dots next to it. It will automatically create a new one from scratch. And that one will be normally okay, buckling restraint wise. Yeah. And again, here the same. Like this. Same. Need to do the same here. So let me just quickly do that one directly. Click on the three dots. I'll need to deactivate it first. No, it's already deactivated here, so that's okay. Okay. That's okay. I'll just need to activate it for these two again. The other ones are okay. They don't have a column in the middle, but the first and the last one do. So let me just quickly clean that one up. And that should be it for the bow imperfections. So it will create a new one, and that's okay. Okay, so activate the bow for bar Y and also for ZZ. Save. Like that. Okay, so the bow imperfections are defined. The global and the local ones are defined. Now we can link them to the nonlinear combinations, but before we can link them, we'll need to have nonlinear combinations. We don't have any. If you don't have any, then SCIA Engineer asks you to define one. We don't want to define them from scratch. We just want to use the same one we have from our linear combinations that are based on the Eurocode with the proper coefficients. In reality, the most precise and the best approach is to copy them all, but it's time consuming. So for the purpose of this webinar, I will only copy one, only one, not all of them, like this. I click on OK. Why is it time intensive? Because you'll need to multiply them by 4. So imagine if you have 50 nonlinear combinations, they become 200. Because you have to consider the 4 directions. I will explain it in a moment, but keep in mind, you'll need to copy them 4 times for the 4 directions, like this. Yeah. This is the story of the global imperfection plus x minus x plus y minus y. So I'll start with plus x. So I go to global imperfection and I say, use those inclination functions that I've defined. For dx, okay, direction x, I will use the inclination for direction x. In the z direction, it will follow, so in the height, it will apply that inclination for the x direction. So the sense is plus. I'll need to do the same, but with the minus sense. So for global imperfection, I'll do again inclination functions, and I will use I def x, but this time the sense is minus, like this. And now we need to do the same for y. Global imperfection, inclination functions, the z. Sorry, for y. So I don't need to consider the x one anymore. Never do them for both directions at the same time. So you'll only need to consider one direction at a time. So the plus y, I will do also the minus y, and that should be it for the global imperfection. I def y, but this time the minus signs, like this. So that's it for the global imperfection story. There still remains the bow imperfections. Remember, we've defined them in the buckling groups, the Eurocode 3, those bow imperfections that we've defined for Y, Y, and Z, Z, but they are still not linked to the nonlinear combinations. And that can be done by just saying, okay, use the bow imperfections that are defined in my buckling data. And that's all. Now you've linked them, and that's it. So the first step was defining those inclination functions, applying the bow imperfections in the buckling settings, and one of the last steps is linking them in your nonlinear combinations, and that should be it. Now you can run a nonlinear analysis, which is in fact a second order calculation. Now, during this calculation, your entire structure will be put under those inclinations in the 4 directions, and it will also apply those bow imperfections. So this is the second combination, this is the third one, and this is the fourth one. So you can imagine the more nonlinear combinations you have, the more time it will take. So I'll click on OK. Let's have a look at the steel code check. Before I'll have a look at the nonlinear results, which is the second order results. Let's just have a look at the linear results. And let me just quickly hide the wind bracings, because the nonlinearity that they only work under tension is neglected when you do a linear analysis. So they can still get under compression, which causes them to buckle. So I'm not interested in seeing that. I'll click on all and then refresh. So this is the results you would get if you just do a linear calculation, a first order calculation. We see several members failing due to that the normal force is in fact bigger than your end critical resistance, your buckling resistance, which gives you the unity check, the famous 999 unity check. But thanks to the fact that we've done the second order analysis, we can neglect flexural buckling. So this is the reward you get by doing a second order analysis in which you apply global and local imperfections. Just simply activate that one, and the buckling check will be neglected. So if I now execute that same steel code check, but this time for our nonlinear combination, let me just pick one randomly. I could create a clause in which all of them are considered, but let's just pick a random one, and we see everything is now okay. This is a more precise calculation, and the added value is that you don't need to wonder or think about the buckling factors. You can neglect it entirely. How do we neglect it within SCIA Engineer? By activating that tick box, we basically put a buckling factor of 0.001 to all members. A buckling factor of 0.001 will lead to a huge N critical Y, N critical Z, which basically means that the buckling check will never fail. You see here a very, very huge N critical, thanks to your buckling factors, which are in fact 0.001, which is explained here. And that's allowable if you do a second order analysis. So that's how, the workflow is for a second order analysis. It's basically the majority of the work lies in the defining of those imperfections. And once those are defined and linked to your nonlinear combinations, it's just clicking on a button and then running the analysis. Now, there are some hurdles you could encounter during this. It happens, and it will happen to you guys as well, that you run a nonlinear analysis, and during the analysis, it stops. It cannot proceed. There is no equilibrium. That's basically because your structure is failing. Your structure cannot carry the applied load. It's failing, and your second order analysis therefore cannot find any results. It's unstable. In those cases, it's really interesting to execute a stability calculation in order to find those weak elements and adjust them accordingly. Usually it's either a member that is buckling by the given load, or you have too many hinges in your structure, which leads to rotations, too many rotations, which then leads to a mechanism or to instabilities that your member is just rotating around its own axis, for example. So in those cases, stability analysis will help you out in finding those weak elements. Okay. So this is a second order analysis via path 2C. The next part is, and the final part, I see I'm almost over 1 hour, so I maybe need to speed it up a bit, but I'll try to give you guys the most important information regarding the SLS check, so the relative deformation check. What is the difference between an absolute absolute deformations and relative deformations? Absolute deformations are in fact your total deformation. Your entire column is moving with the top node, for example. Relative deformations are your deformations relative to a reference line. I will show it in a picture in the next slide, what that reference line is and how it is defined. So here we can see a beam in which I compare the absolute deformations, the red one, with the blue relative deformations. You can see that between the red triangles on this dialog, in which you define your bone perfections, but also your deflection span, you can see that these red triangles are a solid line. If they are solid, it means it's a fixed point. And for your relative deflection, it means your relative deflection will be 0 at these two positions. There will never be any relative deflections there. That's what you see right here. You see, in fact, a reference line that is drawn from those two 0 points. That reference line is, in fact, your 0 line. So if your absolute deformation is on that 0 line, your relative deformation is also 0, in fact. So your relative deformation is nothing more than your absolute deformation transformed or referenced to this reference line for your relative deformation. Nothing more than that. That's what you see right here. So your total one is 37.4, but relative to this line, it's only 28.4. And the check is nothing more than these relative deformations divided by your deformation or your deflection limits, which are defined right here in a relative way. Now you can say 1/200 or 1/360, which means the span length divided by 360, that amount of millimeters is your limit. And that gives you the unity check, in fact. The first one was for fixed, which is one of the use cases. And the second and last use case is a cantilever, which means fixed and free. In case of a cantilever, it's the reference line is parallel to your member line, but it starts at that fixed point. Meaning, if that fixed point moves 20 millimeters in absolute deformation, it means at that 20 millimeter deflection, that point, that's your 0 line, your baseline. That's what you see right here. Huh? You see an absolute deformation of 396, but due to the fact that your reference line, your reference point, your fixed point has moved 2.4, you just subtract it from your absolute deformation, and that gives you a relative deformation of 367 millimeters. So those are the two use cases. This is quite easy to validate manually. You just look at your fixed point. What are the absolute deformations there? Well, your relative deformation will be your absolute minus that deformation right there. While for the other one, you'll need to construct a reference line, and based on that reference line, it will be 0 or not, or higher or lower. So the deflection limits can be defined for the total loads and the variable loads. So SCIA Engineer is able to determine within your combination what are the deflections coming from your variable loads, and also what are the total deflections, so coming from the entire combination. So yeah, that's quite straightforward, I assume. The length of your span divided by that limit, which I've shown you in the previous slide, that 1 over 360 of 1 over 200, that gives you the limit value in millimeters. So that's the story for total loads. For variable loads, it's the same, but you use the variable loads limit instead of the total loads limit. And the SLS check is nothing more than your relative deformation divided by these limits, which you see right here. And your final unity check is just the maximum of those 4. There's also a way to counteract your deflections by introducing pre-camber. There are 3 types. For a cantilever, there's only one, a linear one. You can imagine it as putting your entire beam under an inclination, like this, for example. So this means that the deformations can go up to 50 millimeters before it becomes horizontal, for example. The same can be done for a fixed span, which you see right here, either by a parabolic camber or a bilinear camber. This is often achieved by welding 2 beams with each other in the middle, for example. The overview of the workflow is, you'll need to define your limits in the buckling groups. Optionally, if needed, if you want to use camber, define it there as well. Calculate the project and execute the check. So let's have a look at it in SCIA Engineer. It's quite straightforward. It's just looking at the deflections, comparing them with the limits, nothing more than that. So let me just pick a combination. It has to be an SLS combination, of course. And let's just have a look at the overall unity check. So the maximum unity check. So for this member, it's 0.69. If I click on preview, I can see it in an output table with all the details. So here we can see the different deflections, the different relative deformation for UI max. UI max is in fact the total deflection. UI var is only the deflection caused by the variable load cases within the combination. That's the difference between both. So you see it for UI and for UZ, and the same for the limit. You have a limit for your total loads, which is limit UI max and limit UZ max. And you have a limit for your variable loads, limit UI var and limit UZ var. And the check is nothing more than dividing, for example, UZ max 8.7 millimeters by the limit 40 millimeters for UZ max. So 8.7 divided by 40 millimeters gives you 0.22. And the check overall is nothing more than the maximum of these unity checks. If you've defined camber, you can see those values right here. I can show it, how to define it and how to adjust those limit values. Just select your member. It's defined per buckling group. So if multiple members, such as here, multiple members are using BG3, so they will all, let me close that one, I misclicked. They will all use the same setting. So BG3 are the following members, for example. If I go to their settings, you see them also all displayed in the next dialog. So all the members that are not grayed out are BG3. And under deflection, for deflection Z, for example, I can define the limits. By default, it will use the limits from your steel setup. So in the steel setup, there is a central place to define them. This gives you the added value to only define it in one place, and every element will use it. But you can modify it per buckling group if needed. So here you can say, I want to define them for all spans of BG3, which means BG3 has 2 spans, span 1 and span 2, and you can define them by means of these 2 values. You could also opt to divide them per span. You could say, no, I want that this span has value A and this span has value B, for example. So if you use per span, you can do it, like that. Now, I don't get why I only see one span here. Okay, I get it. It has two segments, but in fact it has one span. But if I activate this one by making it independent and saying, okay, now it has two spans, span 1 and span 2, I can give them individual limits per span. And those limits will then be displayed here in the check. It will inference the check directly. So from setup for all span or per span. Let me just put it back to from setup. The camber can be defined here. You can say just use the setting from the setup, which is one of these four. Or you could say, no, I want to modify them manually only for BG3. So I can say I want to input the camber as a bilinear or parabolic. Let's just use parabolic, and I will give it a camber value of 10 millimeters, for example, for the first and second span. Let's just make it one big span like this, 10 millimeters. And if I click on save, all these members will now have a camber, and I can visualize it. So if I go to the SLS check, let me just quickly just run the check, and we will see that the camber has been applied here. And we can also visualize it. So if I go to deformation UZ, we see here camber dxuz, which means show me the camber for every section position. So show me the camber value for every section position. That's what you see right here. But you could also say, no, just show me the camber value. I don't want to see the curve, just show me the value. If you have multiple camber values and you want to show it in one picture, you could do it like this, for example. It just shows you the maximum value of your camber per member. That's basically it. I can go a bit more in detail, but in fact, it's all described in our online help regarding the camber design. There is a way in which you could say, I don't want to input a value. I don't know what my camber value should be. Let's the engineer calculate the optimal camber value based on the deflections of every combination key I have in my envelope combination. So that can be achieved by putting it into design camber. You have to define your shape. And then there are some boundary conditions for your design camber, some parameters that go along with it. The first one is your minimum camber. If the design camber calculates a camber value of, for example, 5 millimeters, it will apply, which is below the minimum threshold, it will apply the minimum camber. This is, for example, if your fabricator has the minimum value the machinery can produce of 10 millimeters. In those cases, you could use this one. If you don't want to use the minimum camber, you could put it to 0.1 or something like that. The camber limit, this is putting an upper limit on your camber. Imagine if the calculated camber is 120 millimeters, and you set here an upper limit of 100, it will use 100. It's an upper cutoff of your camber. And the round camber, these are rounding your cambers. So basically, if it calculates a camber value of 6.5, for example, it will apply 10 millimeters, for example, or it's an increment. In fact, it can only apply 5, 10, 15, sorry, 20, 25, and etc. So via this way, you can define your increment. And that's all you need to define in order to let the engineer design the camber for you. In this case, the SLS check is already okay, so it will not design a camber if the check is not failing. It will only design one if it's already failing. It also takes into account that once it applies a camber, that your check will not fail in the camber direction. It could be that your unity check is, let's say, 1.2, and by applying the camber, it becomes 1.5 because you make the deflection even worse in the camber direction. So it's quite, sophisticated. It takes into account a lot of things in the background. Okay, that's all for today's session. If there are any questions, I'm more than happy to answer them right now. Let me open the questions panel. So feel free to type out your questions if you have any. Thank you all for your attention. So let's have a look at the questions.